Okay, hello everyone, and welcome to this afternoon full of talks on calculus and algebra, or more plainly, mathematics. My name is NFractionalD. I'm the manager of calculus and algebra at Wolfram. And this afternoon, we have a bunch of talks on various themes. I'll give the overview presentation on what's new, basically in 13.2, and then Adam Strasbonsky will speak about fast polynomial algebra, high performance. Then there'll be a talk on fractional calculus by Tigran Ishkanian, a fourth talk on differential equation solving, a staple topic for any conference. And then finally, we'll have a more education-related talk by Itai on changing variables as a topic. So do stay with us. I do appreciate your coming out on a Friday afternoon at the end of a long conference, having heard so many talks. So if you can take a few more talks, wow, that's great. Okay, so calculus and algebra has continued to evolve in different directions over the last few years. And what I'd like to give is a broad picture of where we are right now, where we're going. And to do so, I'll pick a few themes which have been central in the last year since we last met. So let me begin now by giving the plan for my talk. So I'll begin with polynomial algebra. We are calculus and algebra, but honestly, we have mostly done calculus so far because people love calculus. But algebra is important. So we are back to very fast polynomial algebra algorithm development, dramatic speed ups, and I'll talk about that. Then we go into calculus, usual string of things. There's fractional calculus, asymptotics, Laplace transforms, differential equations. And then I'll transition over to a slightly more applied theme, engineering. So we are basically a pure math team. We try what we can, but we are basically a pure math physics team. But now we're trying to move towards engineering, see, can we take on a challenge? And I'll describe a small experiment which has proved to be quite successful in this area during the last few months. And if there's any one area where you can claim we are really applied, it's linear algebra. So the next theme will be talk about linear algebra and so-called structured matrices. And then finally, documentation, which is so important for us. And then online courses, we've got a huge catalog of courses coming up in the next year. So I'd like to talk about that. So let me begin now with fast polynomial algebra. So the main point is that there are dramatic speed ups for integral polynomial operation 13 point. Integral polynomial meaning that you have a polynomial with integer coefficients. And of course, when you do something in algebra, it affects hundreds of functions, but the most important ones are listed over here. So on the polynomial side, we have polynomial GCD, factor, factor square free, resultant, discriminant. Those are such basic functions for algebra that anything you do over there is A, risky, and B, very, very, having very, very wide consequences. So I'll talk about that in just a minute. But on the linear algebra side, wonderful new advances in linear solve, row reduce, inverse, null space, matrix rank, determinant, and matrix power. And all this for matrices with polynomial entries. So as an example of one of these, I'll just take one example. So I'm going to begin by defining a random polynomial function. Okay, so the n over here is the degree of the polynomial, and the coefficients are pretty large from negative 2 raised 10 to positive 2 raised 10. And then what we do is we take that function and generate a large matrix, a 10 by 10 matrix, each of whose entries is a polynomial of degree 100. So that's a pretty big matrix. And that's the matrix over here. Each entry is degree 100, and it's 10 by 10. In version 13.2, the determinant function takes around 0.3 seconds on my machine, not very fast machine, and the leaf count is 5,000. Okay, that looks correct because it's an expanded polynomial. The leaf count is around 5,000 is correct. How about 13.1? Well, different story. Even the fastest timing on my machine is 117 seconds, and the leaf count is 5 billion. And even to find the leaf count of that took some time, at least when I tried it. So we have a huge dramatic increase over here. And of course, what we've done is to take this simple setup and do a large number of benchmark tests for the new functionality. So we actually have a collection of tests which show us that there are performance gains all around in algebra. But just a small sample over here Let's talk about benchmarks over here. So you see two plots over here, and they are both timing plots. Don't worry about details. The plot legend is simple. Orange is 13.2, gray is 13.1, and their timing, so short is good, tall is bad, very short is excellent, very tall is terrible. Okay, and keep in mind these are logarithmic plots. So there are dramatic speedups all over the place at all exponents in basic algebra. And the question is, how do you do it? Well, we use the Flint library for doing this. There's a fast number 3 library. But it's much more than that. Actually, we have Adam Stresbonsky, who'll speak a little later, who'll talk about this. But basically, we have built a layer of function on top of this to get the real speedups. So it's a combination of Flint, Adam Stresbonsky, Danny Lichtblau, the other expert in polynomial algebra. That's a magical area that only they understand. And of course, our excellent QA, which continues to do excellent work over here. So Adam will speak about that. So let me now go on to the next theme, which is fractional calculus. So we introduced fractional calculus in 13.1. And what this fractional calculus is, it's a combination of the two operations from calculus, derivatives, and integrals. And you put them together, and you get a fractional derivative operator. Now, when Newton and Leibniz discovered calculus a long time ago, there was a long controversy who discovered it. Fractional calculus, there are no problems. Everyone can discover their own derivative when we give it their name. Okay, so there are tens of definitions floating around. We picked two. A fractional D is the Riemann level D, and CaputoD is very popular. That's CaputoD. So just two definitions for fractional derivatives. Here's fractional D. The definition is a mix of derivatives and integrals depending upon the order, the fractional order, which could be any real number. And so an example of that is, let's say, I would call the hello world example of fractional calculus. Find the fractional derivative of x squared of order 1/2. And you get an answer over here. And why would you believe that answer? I mean, so what you do is you do it again. 1/2 plus 1/2 is 1. You get back 2x. That looks good over here. Okay, so fractional calculus is very intuitive, very close to calculus. It merges beautifully with what we do. And on the other side, we have CaputoD, which is slightly different because we kind of basically shave off some initial values over here, because Riemann level D has got some problems that the derivative of constant is not 0. That's not good, okay? So this happens with CaputoD, that you do get a 0 derivative. And it's very useful for solving fractional differential equations because it interacts really quickly very well with the Laplace transform. So here's an example with a CaputoD instead of a D. And it's like a harmonic oscillator, like a damped harmonic oscillator, and you get back a beautiful solution in terms of the so-called Mittag-Leffler function. So Mittag-Leffler is the exponential function of the fractional world. So the current paradigm is that we have three things to do. We have symbolic, 13.1. In 13.2, we have numeric fractional calculus and asymptotic fractional calculus. So on the numeric side, we have two new functions. There's NFractionalD, which is the numerical analog of fractional D, and NCaputoD, which is the numerical analog of CaputoD in 13.2. So here's a fractional D from 13.1. You might think it's simple for sin x, but it's not. It's hypergeometric PFQ. Find the value at a point x over here. Try with NFractionalD, the new function with 0.3. That's 0.3 over here. You get back the same answer. Plot the derivative. You get the usual calculus over here. And the way it works is internally, we just change variables. Because the fractional D has an indefinite integration in it. We change variables, make a definite integration, pass it and integrate, and we are done. Okay. So we have these nice new numerical derivatives over here. Okay, so that's numerical fractional calculus. And on the asymptotic side, we have support for solving linear fractional differential equations in 13.2. So we can find approximate series solutions, but these are not power series. they are kind of Puso series. They've got fractional powers in them. Okay, so if I take this matrix system over here, we have vector variable support over here. You take a matrix, take the order of derivative to be close to 1, 16 over 17, take some initial conditions, set up the problem, and you say, I want 20 terms over here. You get back 20 terms in your asymptotic expansion. You plot it. It looks pretty much like a classical solution. The nice thing about asymptotics is that you can stay as close as you want to classical calculus and never feel the difference. And if you're an expert in this area, you'll tell me, oh yeah, but I could have taken the exact solution away and done a series expansion. Sure, you could, but we also have an extension to polynomial coefficients, which Aram Manaseli will talk about. So there'll be 2 talks by Tigran Ishkhanian on a broad overview of fractional calculus and Aram on differential equations from different standpoints a little later. Okay, so that's about fractional calculus. And I now go on to a function that we introduced some time ago, asymptotic. So the mission of asymptotic was to find a nice approximation. Now, the whole field of asymptotics is a bag of tricks, okay? Someone publishes a paper with one term which they found out, then everyone admires it, then they go on the next one, just goes on that way. That's okay, but a long time ago, the classical masters, Cauchy and Weierstrass, taught us not just about finite sums of approximation, they taught about infinite series. So the question I asked myself was, can asymptotic return the full power series expansion of a function? So in 13.2, we can actually do that. So here's the asymptotic function, like the series function. That's the function, like a geometric series kind of thing, z comma 0. So it's an infinite expansion around 0, and you get back the geometric series. Now, of course, you might say, okay, that only converges in the unit circle. So if you say generate condition goes to true, you get back the exact answer for the full problem. And what's happening underneath is we're using series coefficient to compute the nth term, and some convergence to the convergence testing. So it's just those two put together. In fact, what happened was just that I'd seen Maple 22 advertised as a formal power series. Now we can do it too. So frankly, it's just a response to Maple's formal power series. Some examples of that. So here's the asymptotic expansion of sine z, but now it looks nice. A series coefficient is good, but the output is not very nice. This is a textbook output for the sine expansion. The next one surprised me when I saw it. You get back Bernoulli B, but then remembered it's just the exponential generating function for the Bernoulli numbers over here. So you have a nice big function name over here, exponential generating function Bernoulli B. You get back exactly the same function that you started with over here. And another nice example is an algebraic function. Clearly, the problem at z equal to a quarter, and you get back the domain of convergence over there. And the plan is that we want to use this functionality to make asymptotic d-solve value better by giving the full power series solution for these cases. So that's the goal of this whole program. Try and make asymptotics exact, not just approximate. So you have the approximate and then the exact solutions both available to you. Okay, now one thing we have worked on quite a lot in the last few years is inverse Laplace transforms. And we did the Bromwich contour integral method, numerical evaluation, all that's been very successful. But the problem is, whenever you do something of this sort, someone says, oh, you can't do that exam, you can't, that's because some famous benchmark. So believe it or not, beneath every successful symbolic function is a table lookup designed for such users, okay? Right, so one of the most famous benchmarks in Laplace transforms is a book by Overetting and Buddy, well-known table. And in version 13.2, we cover all the 1200 inverse transforms in this important benchmark. That's a lot of work checking each of them. It's an ancient book, never been updated, lots of minor errors, lots of puzzling things, but we have done it now. And as an example over here, here is a pretty, I would say, non-trivial example of a gamma and a Bessel function. You're now in Laplace space, in the S space. So that's the kind of complex plot over here. We compute the inverse Laplace transform in 13.2. It comes back in a flash. It's just table lookup. We're doing no work over here. And we check the answer numerically. And this over here, because got the inexact number over here, we'll use the numerical algorithm from earlier release. So that's a perfect check of the symbolic answer. So you can do exact asymptotic numerical Laplace transforms really well in 13.2. That's a long project. We'll close out very soon, hopefully. And finally, differential equations. So, we've been doing lots of differential equations for a long time. And we've done Hoyne equations and all kinds of stuff, which is fantastic. But honestly, people have complained about something else. They told us that, we can't solve college textbook problems well. Okay. We knew it. We tried to ignore it for some time, but we couldn't do any more. So in 13.2, we've done something that will make a lot of people happy. So the point is that these linear ODEs with constant coefficients are really important applications. So that's what people use all the time. The engineers call them LTI systems. And that's a big deal for them. That's all that they know about. And the world runs on them, okay? Right. Now, the nice thing over here is that there are two parts, the left-hand side, very algebraic, right-hand side. And the right-hand side, the so-called inhomogeneous term, has what are called the forcing function. That's what keeps the system from kind of, becoming steady state. And this is where the problem lies. So in version 13.2, we return simpler solutions for these inhomogeneous ODEs. And there are about 3 or 4 published reports with probably 100, 150 examples. We have cracked them all in 13.2. So an example that's become better here is an inhomogeneous third order constant coefficient linear ODE. That's third order over here. That's the right-hand side, a very typical right-hand side, which many people can do by hand. And that's the answer in 13.2. And you say, okay, that looks quite bad, right? Well, let me show you the 13.1 answer. And you can check it on your own if you like. There you are. Okay, that's the answer 13.1. No wonder they were complaining. Okay, right. So I think this will be appreciated by many users, and hopefully I'll stop spending a lot of time addressing those complaints from them. Okay, so now the question is, I said engineers use them, but do we really know? I didn't know, honestly. I'm not an engineer, I'm a mathematician, and I trust engineers, but I don't know what they do really. So some time ago, he said, okay, let's take a typical book on engineering electric circuits and see how far we get with our functionality. Okay, so this is a project which has been going on for some time, our electric circuits project. So of course, if you study, I have not studied, but if you're an electrical engineer, you begin with electric circuits. And what you've done is to take a popular textbook. When I say popular, I mean having the best and the most number of Google reviews with at least one student saying something nice about it. Okay, and that book is a book by Alexander Sadiku. And if you look at the table of contents over here, they begin with the introduction, then they go to algebra, and they tell you, okay, now I'm going to calculus. So it's algebra followed by calculus, exactly what we do. So what we said is, okay, let's try and solve every problem in this book using mathematical and system modeler. And we have now got around 800 examples of these circuits with us. It's going really, really well. So these should be available in some form or the other in a later release of Mathematica. So an example, let's design an analog computer which solves a differential equation over here. So we first use system modeler, like over here, set up the circuit. I don't do it, the intern does it, Hawken Orozco. Run the simulation, get the plot, repeat the same thing in Mathematica, but now resolve value and get back just the same answer. So 800 examples checked completely with our functionality, both software doing really well. And so now I turn to the one area which I think has got real promise for applications, which is linear algebra. So we have these structured matrices which are really easy to specify, but hard to work with in the past. So the idea is you have a small specification which gives you a large output. And the key point is don't do the full output. Suppress it, keep it with you, store it, and compute. And there are two of them. There's Vandermonde and there's Cauchy. So here's a van der Waals matrix. It requires only a vector of length 3 to specify to get a 3 by 3 matrix. Cauchy's requires 2 vectors. And you see over you just get back a blob. Why? Well, it doesn't matter. Most people just put a semicolon, right? When you define a matrix, the first thing you do is put a semicolon after it. We never see them really. So here then is the first matrix, van der Waals, looks polynomial. That's Cauchy, computed determinant. Nice example to show that it works just like any other function. What are the nodes? You can work it out. So these matrices know everything about themselves. They are self-aware. They know what they are. And you can ask the matrix, okay, what are you good for? And it'll tell you, okay, I'm good for the following functions. Okay, so it actually has a list of functions built into it, which you can figure out for using in your work. And these matrices are really good for solving so-called interpolation problems. So an example here is a rational interpolation function problem. So you pick the idea is you pick a set of points of the complex plane, for example, specify some values for the function that you want to build at those points, prescribe some poles, singularities for the function, build the Cauchy matrix over here, like over here with the points and the poles, use the values to work out the coefficients of a rational function, find the rational function, plot it along with the points, and lo and behold, you checked everything in just a flash. So these new matrices are key to many interpolation problems in the real world. Okay, so I think that's mostly the core mathematical part, and the remaining time I'll talk about 2 other things, which is documentation. We continue to do lots of documentation. So we've added examples to around 100 special function pages, application examples. For fractional calculus, we've tried to do everything. We did the functionality, we did a webinar, we did a blog post, videos, everything. And now finally, we have a tutorial which you can study on your own on fractional calculus. It's a very nice written tutorial done by the team from who've been working together. And a long time ago, when I didn't do so much management, I used to write things. So I actually wrote a tutorial on dsolve in 2004. It was not updated. And this year we updated. So you have a fully refreshed tutorial on dsolve available to you. Okay, so documentation is really a very big area for us. And as a team, we try to do development. We try to do benchmarking. You saw that. We try to do documentation. And the last thing is we try and do courses. So latest course, thanks to Wolfram U, is a course on elementary algebra. So this is for middle schoolers. I believe, I will say this, if you can solve the problem of teaching algebra in this country, you'll have saved a lot more money than by doing anything else. So this course makes a small attempt to teach algebra the way we think it should be, which of course may not be the right way, but we won't admit now, okay, right. So lots coming up, the probability course coming up, statistics, discrete math, finite math, and then that's it, okay. So I'm done really. And I'd like to thank you all for coming over here, and I'll stop and pause for questions. I'll stop sharing so the next speaker can start sharing their presentation. Thank you very much.